Okay, this video is going to solve the problem. A uniform rod of mass m and length L is pivoted at a point a distance L/3 from the top end as shown below. The rod is pulled back so that it makes a small angle with the vertical and is then released. This is the image they give us. So they give us, a rod, and they give us a pivot point. They tell us that the distance of the entire rod is L, the distance from the pivot to the end is L/3. And they're saying this is the vertical. It creates an angle of theta with the vertical. So based on this information, there are a couple of things we can do. Well, first I'll start with our assumptions. Our assumptions are, that this angle theta is small enough that we can use small angle approximation. So essentially, we can assume that sine of theta is approximately equal to theta. Additionally, we're going to assume that we're on Earth capital, and we are going to assume that there is no air resistance or friction, because that would affect our rod and its motion. Okay, so based on this, there are a couple of things we can solve. So, we can start by drawing a free body diagram of our rod. Then we're also able to calculate the moment of inertia of the rod because we're given its mass. And the distance it is away from each end, and we're also told that it's a uniform bar. So we're going to be able to calculate its moment of inertia either using calculus or by using the parallel axis, and then the parallel axis theorem. We're also going to be able to calculate the frequency of oscillation. So we'll be able to figure out. Okay, we'll be able to figure out I. We'll be able to figure out omega, so the frequency of oscillation. We also know that we'll be able to apply torques is equal to I alpha or R cross F in this case. And since it's an object that's in simple harmonic motion, we also know that in this case dx squared over d squared x over dt squared plus omega squared x is equal to 0, which we can then use to solve for omega. We can figure out the period once we know omega, because period is just equal to 2 pi over omega. And using our torque equation over here, we can figure out alpha, and from alpha, we're going to be able to figure out the acceleration. Additionally, using conservation of energy, we can figure out the energy that the object has, and so we can figure out its velocity right at the very bottom of its trajectory. And then since we know it's alpha and we know how much distance it's traveled, you can use kinematics to figure out the time it would take to travel a certain distance. So we'll also be able to figure out time and its velocity, which I just said using energy relations. And since we're going to know the force applied on this object, or we can figure out the force applied on this object using our free body diagram and the distance that it's traveled, we can also figure out the work done by the object. Okay, so given that, let's begin our problem. I think I left the eraser somewhere, so, okay. Here we go. Alright, so the first question is, using integral calculus, show that the rotational inertia for the rod around its pivot is ml squared over 9. So we're going to use, well, as it says, oh, it's right here. Okay, anyway, so as it says, we're going to use integral calculus. And so we know that for moment of inertia, that is equal to the integral of r squared dm. Where basically we're adding up the radius. Every little bit of mass is away. To figure out like how much inertia it has. And so what we can do in this case is, since we know it's a uniform mass, we can use a variable lambda, and we're going to use it to represent the mass over the distance. We're going to use it to represent the mass over the distance. And over here, since we're trying to figure it out for a super small mass, so since we're trying to figure it out over the entire length, and we're going to break this up into infinitely tiny parts. Each distance will have a length dx, and each little dx will have a value of dm. And so what we can do is we can just say that lambda is equal to dm over dx. And solving for dm, what we want to do is we get lambda dx is equal to dm. Now r is in terms of x, right? Because r is just our length. And so what we can say is this is equal to x squared. X will be our variable for length, is equal to lambda dx. Integrating this, we get, and then our bounds of integration are going to be over the entire length of the rod, right? So this over here, let's just define this way to be positive. This over here is going to be negative 2/3 L, because this is positive 1/3 L. So we're going to integrate from negative 2/3 L over 3 to positive L over 3. And I'm not going to rewrite it here because I'm out of space, but same bounds of integration. Integrating this, we get that 1/3 x cubed lambda, we're integrating with respect to x, is equal to, from negative 2 L over 3 to L over 3, and plugging this in and pulling out constants, we get 1/3 lambda is equal to is going to be equal to L cubed over 3 cubed minus negative 2L over 3 cubed. And this is going to evaluate to, just going to write it here, this is going to be equal to 1/3 lambda times 9 L cubed over 3 cubed, which simplifies because this cube cancels out with this, and we're just left with 1/3 lambda L over 3 cubed, which then becomes L cubed lambda over 9. And then remember, we got to substitute back in lambda, which we defined up here to be m over x. So this is going to be m L cubed over x to the over 9, and then x is just our length because it's the total mass over the total length, and so we can just replace this with L, and so the L's cancel, this becomes a 2, and then we're just left with mL squared over 9, and that's exactly what we wanted to prove. The moment of inertia is equal to mL squared over 9. Okay, part B says, using Newton's second law in rotational form, Right, but do not solve a differential equation in terms of m, l, and physical constants as appropriate. That can be used to determine the angular displacement theta as a function of time. Okay, well, now we're trying to relate theta. Hold up. So let's start with Newton's second law. So Newton's second law is just F equals ma. In rotational terms, that means that torque is equal to I alpha. Now here it says we're trying to come up with an equation for the angular displacement of theta using this. So what we can do is we can relate alpha to theta, and a differential equation that does that is is the one for simple harmonic motion, where we have d squared x over dt squared plus omega squared x is equal to 0. Okay, so now what we need to do is we need to figure out what I alpha is, so that we can solve for alpha and plug it in over here, because this over here is just equal to alpha, or accelerator is just equal to alpha. And we know that torque is also equal to R cross F, which is which is equal to R times F times sine of which is equal to R times F times sine of theta, where theta is the angle in between them. Now over here, if we draw a free body diagram of our rod, we're going to see that right here in the middle is the center of mass. The forces acting on it are gravity, so mg, and this right here is theta. So the direction that's actually going to be pulling it back to the center is going to be this distance here. And that distance is equal to mg sine theta. The other forces acting on it are the normal force because of the pivot, and pulling down are mg cosine theta. But we only care about mg sine theta since that's the restoring force, and since it's the restoring force and it's going downward, and we're defining downward to be in the negative direction, mg sine theta is going to be negative. Okay, so now going back to this definition, R cross F, the force is going to be pulling it that way, and this is the radius. So this angle right here is 90 degrees, and sine of 90 degrees is just 1. So this goes away. So we're just left with R times F. Now, we're going to treat this object, we're going to think of this rod in terms of its center of mass. So when we talk about R, we're only concerned about the radius from the pivot to the center of mass. And in this case, the center of mass is going to be at L over 2. Because it's a uniform rod, it should be right in the middle. And the pivot is at L over 3. So this distance here between the center of mass and the pivot is just going to be L over 6, which is going to be equal to RR. Okay, so what we have here then is that R times F is going to be L over 6 times mg sine theta. This is a different theta than the one that we used for R cross F. The R cross F theta is the angle between R and F. The mg sine theta angle is the angle between is the angle of the rod from the vertical. And so using small angle approximation, we're assuming that theta is not very large. We can just assume that sine of theta is equal to theta. So this is about equal to mg theta. Okay, and this is equal to I alpha. So solving for alpha, we get that mg sine theta divided by I is equal to alpha. Making some room here. Erase this for a sec. Okay. We see that mg sine theta is equal to alpha. Now that we have alpha, we know that I just erased this equation. We know that this is true. And so over here we can alpha is just equal to d squared x over dt squared. And so we can rearrange this equation right here. And what we get is d squared x over dt squared plus L mg theta over 6i. And this should be negative over here because mg sine theta was supposed to be negative. And so this is equal to 0. So this is our differential equation for part I. Now, part 2I, I guess, says, using differential equation from part B, show that the period of oscillation for the rod is given by the expression T is equal to 2 pi square root 2L over 3G. Okay, so then using this, so it says find the period. And the most important thing for the period is knowing that T is equal to 2 pi over omega. Now what we need to do is we need to find omega. And we have this expression over here. And the general form is just the acceleration plus omega squared x equals 0. And this is basically the same thing, because remember, since we're doing this in terms of angular terms, theta is equal to our x, which means that this is equal to our omega squared. So omega squared is equal to LMG over 6i. And since we know, and we can just plug in for I, which we solved in part A, we solved that I is equal to ml squared over 9. And so we can plug that in over here. So LMG over 6 times ml squared over 9 is going to be equal to, so these L's cancel out, this M cancels out. What we're going to be left with is 9G over 6L, and then this simplifies to 3G over 2L. And this is equal to omega squared, which means omega is equal to 3G, square root of 3G over 2L. What we want to find is period, though. So T is equal to 2 pi over omega. So T is equal to 2 pi divided by the square root of 3G over 2L, which is simply just 2 pi square root of 2L over 3G, which is exactly what we want to find. Okay, so then part C asks us part C asks us, an experiment is performed with a thin, uniform metal rod of different lengths, each pivoted around a point 1/3 the length of the rod from the top end, and used to make a physical pendulum, as shown in the figure on the previous page. Each rod is pulled back so that it makes a small ankle with the vertical and is then released, and the period of oscillation is measured. The data are recorded in the table below. And the table just says that we have L and we have period, and we have 0.5, 1.5, 2, 2.5. And this is 1.2, 1.6, 2, 2.3, and 2.6. Okay, so then it says, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity g. Okay, so what we want to do here is we basically want to linearize the data. And a linear form, or a linear equation, is equal to, is in the form of y equals mx plus v, right? And so we know that L and period are related by what we did in part B, where we have t is equal to, no, this should not be p, this should be t, sorry. We know that t and L are related by 2 pi is equal to 2L over 3g. This is exactly what we just did in part B. And so what we want to do is we want to get, in this case there is no like extra constant b term, so we're just going to get rid of that for a second. And we want to make it look like this. And so we want the graph to be in terms of x, which in this case is our L, since our L values are changing. So what we want to do is we want to, since our L values are changing, so we can rewrite this equation as equal to 2 pi times the square root of 2 over 3g times the square root of L. Now we almost have x, but we want to get this on its own. So what we're going to do is we're just going to square both sides. So t squared is equal to 4 pi squared times 2 over 3g times L. And now this is exactly what we have. This is our y, and this is our x, and this is just equal to our slope. So what we want to graph is we want to graph on the x-axis, we want to graph L, and on the y-axis, we're going to want to graph t squared in order for this to be a linear equation. Now, what we want to do then, it says that the slope should be able to use to calculate the acceleration due to gravity g. And so we see here in our m of this graph that g is involved. So now let's just rewrite this in terms of, let's just rewrite this so that the slope is a little bit cleaner. And what we can do is we can just divide by L. So what we're going to get is we're going to get t squared divided by L is equal to 4 pi, I'm just going to write this as 8 pi squared over 3g. So the slope that we're going to get is going to be equal to this. And the way we can solve for g is then we can just simply solve for g. So then this is just going to become 8 pi times the slope that we get of our graph is equal to g. Now the next part of the problem asks us to actually graph it. And since I don't have a handy dandy paper, I decided to use Desmos. And so what I did is I basically on the x-axis I graphed L, and on the y-axis I graphed the t squared based on the values in the table. And so this is what I got, and then I used the fancy Desmos hack to draw a line of best fit and to figure out the slope, and the slope that it gave was 2.674. And so part E asks us to calculate g based on the slope. So we're given, based on the slope that we found in the graph. So we found in the graph that m is equal to 674. And so basically we just have to plug that into this. So instead of, we're going to replace slope with 2.674, and then I plugged that in ahead of time, and this means that g is calculated to be 9.86. But the proper number of sig figs, it should be 9.9 meters per second squared. And that is